Okay, so now let's start with the chapter on probability. Now, in the earlier classes, we have studied about the concept of probability as a measure of uncertainty of various phenomena. And we have obtained the probability of getting an even number in throwing a die as 3 by 6 or 1 half. Now, the total possible outcomes, if you think about when you throw a die, you can get any one of the six numbers on the top of the die. So it could be 1, 2, 3, 4, 5, or 6. And the outcomes that are in favor of getting an even number are 2, 4, and 6 because there are only three even numbers on a die. So based on that, we can say that the outcome is 3 over 6, which is 1 half. So if you were to generalize this, to obtain the probability of an event, we find the ratio of the number of outcomes favorable to the event under consideration to the total number of equally likely outcomes. And this theory of probability is known as the classical theory of probability. Okay, so finding a simply a ratio. So again, I'll emphasize this point. The main idea about probability is that you're trying to measure uncertainty of various phenomena. It's a measure of uncertainty, and it is a very useful mathematical idea that gets used in many fields, not just of engineering, but in different sciences, in biology and all. Now, in your class ninth, you would have learned to find the probability on the basis of observations and the collected data. And this approach, in which look at, okay, this many, for example, the exam we took off the dice example, you are going to observe how many times you are getting a certain number on the top of the die, or you collect data and then you try to get probability of it, is known as statistical approach to probability. Now, both of these theories, the classical theory as well as the statistical approach to probability, do have some challenges. Now, if you look at the examples, like these theories, we cannot really apply to activities and experiments which have an infinite number of outcomes. This is a huge issue because you have to do a lots of infinite number of experiments, let's say, to be able to get anything based on the classical theory of probability. Now, in classical theory, we assume all the outcomes to be equally likely. So, this is the basic assumption. And if you remember, equally likely outcomes are those when we have no reason to believe that one is more likely to occur than the other. So, in other words, we assume that all outcomes will have an equal chance or probability to occur. Now, to define probability, we have used equally likely or equally probable outcomes. Now, this cannot logically be correct completely. So, another theory of probability was developed by this scientist called A.N. Kolmogorov, a Russian mathematician, in 1933. And he laid down some axioms to interpret probability in his book known as Foundation of Probability, which was published in 1933, so almost 100 years ago, maybe 90 years as of today when I'm making this video. And in this chapter, we are going to study about this approach of the that is known as the axiomatic approach of probability. So before you go into that, and in order to understand this, we need to understand the basic terms. The terms that we are going to focus on are random experiment, sample space, events, and so on. So let's look at that. So let's start with the first term that you need to really understand is random experiments. Now, in our day-to-day life, we perform many activities which have a fixed result. You know what the outcome is going to be. No matter any number of times they are repeated. So, like if you take an example of a triangle, let's say, without knowing the three angles, you can definitely say that the sum of the measure of angles is 180 degree. Now, we also perform many experimental activities where the result may not be the same when they are repeated under identical conditions. So, for example, when we toss a coin, this is the simplest example because you can only have two outcomes, right? It may turn up a head or a tail. But we cannot really say for sure which one of these results will actually be obtained. Will you get a head or a tail? So, such kind of experiments where the outcome is not a given, right? Which outcome will come is not a given, they are known as random experiments. So there are two criterias that we need to apply to an experiment so that it can be called as random experiment. First criteria is that it has to have more than one possible outcome, means of course it needs to have some outcomes. It is not possible to predict which of those outcomes will happen in advance, right? That's the measure of uncertainty. You are not certain what will be the outcome of a given set of outcomes, which should be more than one. So for example, if you look at the experiment of tossing a die, is it random or not? It is random. We do know that it has more than one outcome. There could be one of the six numbers, and we cannot really tell for sure which number will come when we roll a die. So now keep in mind that in this chapter, the word random experiment or the phrase random experiment has just been replaced by experiment. So so whenever the word experiment comes in, you have to think that it is actually referring to a random experiment, unless it is stated otherwise. Now, let's expand this idea of the random experiment a bit further by defining a few more terms. Now, when you do an experiment, we said that it has to have outcomes. Okay, what are these outcomes? How many of these outcomes are there? So let's try to define those terms. Now, a possible result of a random experiment is called its outcome. Now, if we take the example of rolling a die, okay, what are the outcomes of this experiment, rolling the die? Well, you will get either number 1, 2, 3, 4, 5, or 6 if we are interested in the number of dots on the upper face of the die. So the set, remember the set of the outcomes which is represented this is known as the sample space of the experiment. So very simple, sample space simply means the set of the number of outcomes, okay, the set of the outcomes. So the set of all possible outcomes of a random experiment is called a sample space that is associated with the experiment. And keep in mind that the sample space is denoted by the symbol capital S. Okay, that's how we represent it. Now, each of these numbers here, like you have 1, 2, 3, 4, 5, and 6, okay, you can call them as a sample point. So in other words, each of the random experiment is also called a sample point. So keep in mind that the outcome and sample point are in a way same thing, right? Whatever you call outcome is a result and sample point, right? So it's just the two words used for the same thing. Now let us look at some examples for this one. Let's use a different color. So two coins, a 1 rupee coin and a 2 rupee coin are tossed once. Find a sample space. So if we were to do this, you do know that when we flip a coin, either you can get a head or you may get a tail. Now you have two sets of coins, okay? So in the other case also you may get a head or you may get a tail, okay? So in this case, the two coins are clearly distinguishable in the sense that we can speak of the first coin and the second coin. Now the coin, each coin, when you flick it, you can have either a head or a tail. And the possible outcomes could be these, right? You could have heads on both the coins, so which you can represent it as this H comma H or HH. You can have head on the first coil and a coin and tail on the other, so HT, that's the second one. You can have tail on the first coin and head on the other, so TH. You can have tail on both the coins, TT. So the sample space is nothing but a combination of all the outcomes, so HH, HT, TH and TT, and this is how you will represent the sample space of this experiment. Now note that the outcomes of this experiment are ordered pairs of H and T. For the sake of simplicities, the commas are omitted from the order pairs, just because you have to write two brackets and comma, the bracket and the comma, it just makes it difficult, so you represent it in a simple way. Let us look at another experiment. So another question. Find the sample space associated with the experiment of rolling a pair of dice. One is blue and the another one is red. And also the number of elements of this sample space. So two things are asked, right? You have to find the sample space and the how many elements are there, or how many number of outcomes, or how many sample points. When you say number of elements, how many outcomes, how many sample, yeah, how many elements are there in that. Okay, so suppose 1 appears on blue die and 2 on the red die. Now we denote this outcome by an ordered pair 1 2. So what we are doing is, first we are trying to just understand how do we represent each outcome. Okay, and similarly, if 3 appears on the blue die and 5 on the red, the outcome is denoted by the pair 3 comma 5. So if we were to generalize this, we can denote each outcome by the ordered pair x comma y, where x is the number appearing on the blue die and y is the number appearing on the red die. Therefore, this sample space is given by S equals x of x and y, where x is the number on the blue die and y is the number on the red die. Now the number of elements on this sample space is clearly because you start with 1, and then, like, let's say if there is number 1 on the blue die, then you could have the number 1 on the red die, you could have number 2, you could have number 3, 4, 5 or 6, any of these. Okay, so you can see, so this is what is possible. So this is one, if you have 1 on the let's say blue die, then you could have any of this. Now if you just mathematically treat this, then you do know that you need to repeat this 6 times. So basically the number of elements in this sample space is 6 times 6, 36. And if you add, the sample space is given below. So remember that we are following this definition over here. S is a combination of the ordered pair x and y, where the first number is the number on the blue die and this is the number on the red die, and this is what you get as the whole of the sample space. Let's look at the third example. So in each of the following experiments, specify the appropriate sample space. So first one, a boy has a 1 rupee coin, 2 rupee coin and a 5 rupee coin in his pocket. He takes out 2 coins out of his pocket, one after the another. So what is the sample space? 2 coins out of his pocket, one after the other. Now, how will you approach this? So you have to just use some mathematical symbols and ideas from algebra to do this. So you can say, okay, first of all, let Q denote the 1 rupee coin, let H denote the 2 rupee coin, and let R denote the 5 rupee coin. So this is first thing that you would do. So you have H, Q and R. So this is rupee 1, this is 2 and this is 5. Now the first coin he takes out of his pocket could be any of the 3 coins, right? It could be Q, H or R. Now corresponding to Q, the second draw may be H or R. So let's say if he takes out Q, the result of 2 draws may be QH or QR. So similarly, corresponding to H, the second draw may be Q or R. So therefore, the outcomes may be HQ or HR. And lastly, corresponding to R, the second draw may be H or Q. So the outcomes may be RH or RQ. So basically what you are thinking is that 2 coins. So, in the first scenario, let's say he pulled out a 1 rupee coin. Then you could either have Q or he could either have R. In the second scenario, let's say that he pulled out Q, which is 2 rupee coin. Now then he could either have H or he could either have R with that. And in the third scenario, if he pulls out the 5 rupee coin, then again he could have H or he could have Q with the R. Okay, so the sample space that you get is comprised of the 6 combinations. Okay, QH, QR, HQ, HR, RH and RQ. Okay, so the number, okay, so that is the first one. Now if you look at the second, a person is noting down the number of accidents along a busy highway during a year. Okay, now the number of accidents along a busy highway during the year of observation can either be 0 for no accident or 1 or 2 or some other positive integer. It could be any. So a sample space associated with the experiment is S equals 0, 1, 2, dot, 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 which means it could be any number. Okay, let's look at one more example. A coin is tossed. If it shows head, We draw a ball from the back consisting of 3 blue and 4 white balls. If it shows tail, we throw a die. Describe the sample space of this experiment. Again, you have to denote, you have to use some symbols. So first and foremost, you need to denote the balls. So you denote the blue balls by B1, B2, B3, and the white balls are 4. So W1, W2, W3, and W4. Now, okay, so you toss a coin. So let's say if you get a head, okay, once let's just do it over here. So if you have got a head, then along with that head it could be, and then if he pulls out a ball, it could be any of these 7 numbers. So H goes with B1 to B3, and H also could go with W1 with W4. So you will have a combination of HB1, HB2, HB3, HW1, HW2, HW3, HW4. Now if he does get a tail, then you can throw a die. And if you throw a die, then you could have a T with a die with 1 on the face, tail with 2, tail with 3, tail with 4, tail with 5, tail with 6. So this is your sample space. So HBI simply means head on the coin, and BI is the ball drawn. So similarly, HWI means head on the coin and the ball WI is on. Similarly, TI means tail on the coil and the number I on the die. So this just gives you an example of how do you model the sample space given these numbers. Okay. Now consider the experiment in which a coin is tossed repeatedly until a head comes up. Describe the sample space. So the experiment again comes down to how many times do you have to describe the sample space. So in this case, you know that it can be infinite, right? It can keep going on. I mean, in the experiment, the head to come up, head may come up on the first, it may come up second, third, fourth, fifth, and so on. So the desired sample space is H, TH, TTH, TTTH, TTTTH, and so on. Now, here is your exercise. I would recommend that you complete this exercise for you and try to finish this so that you understand and appreciate how to define sample space of various events.